So we're going to continue our study of the introduction to Algebra 1, working through articles number 39 through 52. In our previous two lessons, we covered the first 38 articles, and as I've said, this is simply an overview of the important definitions and signs and terms that are necessary for the study of algebra using Ray's Algebra 1, which is the basic text for our Algebra 1 and Algebra 2 courses. In this lesson, we're going to wrap up this introduction, finishing up through Article 52. In the next lesson, there's simply a collection of exercises to be completed that will test whether or not you understand the concepts covered in Articles 1 through 52. And then we'll be on our way in the study of algebra, beginning in Article 53. All right, so to pick up at Article 39, I'm just going to read through the text that's in your lesson and make a few comments that I hope are helpful, just to help you work through this first reading and study of the elements of algebra. Article number 39. Every quantity or combination of quantities expressed by means of symbols is called an algebraic expression. Every quantity expressed using symbols is called an algebraic expression. All right? Article 39. Article 40. A monomial, which is also known as a term. So the word term means the same thing as monomial. Monomial and term are synonyms. A monomial or term is an algebraic expression not united to any other by the sign plus or minus. Read that again. This is a very important definition. Later on in algebra, one of the topics that gets students most confused is called the order of operations. So if we have a number of different operations, multiplication, division, square roots, exponents, and so on, to be calculated or written in an expression, how do we know which order we're to solve them in? The answer to that question is really found in the definition of a monomial or term. So let's read this again. A monomial or term is an algebraic expression not united to any other expression by the signs plus or minus. So the signs plus and minus separate terms. Okay, that's a very important concept. The signs plus and minus separate terms. All right? Multiplication does not separate terms. Division does not separate terms. Plus and minus separate terms. That's the definition of a monomial or a term. That's very important. Make sure you pay extra attention to Article 40. 41. A polynomial. Polynomial. And these are very simple words coming from classical languages. Mono means one. Nomial comes from the Latin word nomen, which means name. So monomial, a single name, single term. Polynomial, multiple terms. Poly, multiple, more than one. Okay? Article 41. A polynomial is an algebraic expression composed of two or more terms. A polynomial is an algebraic expression that contains two or more monomials, or two or more terms. All right? A polynomial. That's Article 41. Article 42. A binomial. Bi means two. Tri means three. So binomials and trinomials, you can probably figure out what this means. A binomial is an algebraic expression consisting of two monomials, or two terms. A trinomial is an algebraic expression consisting of three terms. Binomial and trinomial are both polynomials. If there was any number of terms more than 3, they would just be referred to as a polynomial. Okay, so that takes us through article number 43. Article 44, the numerical value of an algebraic expression is the number obtained by giving particular values to the letters and then performing the operations that are contained in those expressions. So if we take an algebraic expression, that expression will represent a quantity, but we'll use symbols, we'll use letters to symbolize quantities that are not at the time known. If we give numerical values to those individual quantities and replace the letters with numbers, we can then perform the operations in the expression and come up with a numerical value for the entire expression. Okay, so when we give a numerical value to letters in algebraic expressions, we can then calculate or compute the numerical value of that algebraic expression. Article 45. The value of a polynomial is not affected by changing the order of the terms. The value of a polynomial, the value of the expression as a whole, the value of a polynomial is not affected by changing the order of the terms. Okay? And there's one extra note there in this Article 45. Provided that each term retains its respective sign. Changing the order of quantities or terms within a polynomial expression does not change the value of the expression as a whole, as long as we retain the signs of each of the individual terms. And you have examples there in the lesson. So the order of terms in a polynomial doesn't matter. That's going to be important later on, because when we start to solve problems using polynomials or try to simplify polynomials, we're allowed to move terms around to make that easier for us, as long as we retain the signs, positive and negative, of each term. Okay? And remember, if we see a polynomial made up of a number of terms that are separated by plus and minus, remember that minus is the same thing as plus a negative. So that's how we can retain the same signs by moving things around. If we have minus 3x, that's the same thing as plus negative 3x. Okay, so as long as we retain the signs of the quantities, a negative quantity remains negative, a positive quantity remains positive, we can move things around in polynomials. All right, that's Article 45. Article 46. Each of the literal factors of any simple quantity or term is called a dimension. A dimension. Okay? Article 46. Each of the literal factors, the letters used in multiplying in a term. Each of the literal factors of any simple quantity or term is called a dimension. A dimension is any literal factor in a quantity or term. The degree, down here in number 4, the degree of any term depends on the number or dimension of that term, the number of literal factors, which is the dimension. So if there are 3 literal factors, that quantity is said to be of the 3rd dimension. If there are 2 literal factors in a quantity, that quantity is of the 2nd dimension. All right? This is in Article 46. Each of the literal factors of any simple quantity or term is called a dimension of that term. The degree of a term depends on the number of its literal factors. And then they give you a couple of examples there in your lesson. Okay, so that's Article 46. Article 47. A polynomial is said to be homogeneous when each of its terms is of the same degree. A polynomial is said to be homogeneous, or of the same kind, when each of its terms has the same degree. And as you read through these, you'll see these are pretty simple. I just want to make sure that pronunciation and just a couple of basic notes are clear, because the study is not very complicated. A polynomial is said to be homogeneous when each of its terms are of the same degree. Article 48, a parenthesis is used to show that all the included terms are to be considered together as a single term. Parentheses are used to show that everything included inside of those parentheses is to be treated as a single term in the larger algebraic expression. Okay? So to avoid confusion, we use parentheses to show everything here is a single term. Even if the quantities inside of the parentheses are separated by plus or minus signs, it's still to be considered as a single term. Okay, so we use parentheses to avoid confusion. Article 49 you can really ignore. It's just explaining a sign called a vinculum, which we're rarely going to use. You may see it in your textbook, but outside of this textbook you'll never see it, so it's not that important. Article 49. Article 50. Similar or like quantities are quantities composed of the same letters affected with the same exponent. So not just the same letters, but the same letters with the same exponents. Article 50. Similar or like quantities are those which make use of the same letters with the same exponents. So just because the letter A is in two quantities doesn't make them like quantities if one is a squared. All right? So similar or like quantities are those with the same letters having the same exponents. Article 50. Article 51, a reciprocal. The reciprocal of a quantity is simply one, or unity, divided by that quantity. So if we were to take any quantity, say a squared, and we wanted to find the reciprocal of a squared, we would simply write 1 over a squared, and that's the reciprocal of a squared. All that a reciprocal actually is a fraction that's inverted. So 1 over a squared is this quantity inverted. And the reason why I say that is because a squared is equal to a squared over 1. So a squared over 1 inverted becomes 1 over a squared. So our definition in the lesson of a reciprocal is unity divided by any quantity is the reciprocal of that quantity. But very simply, all you need to know is the reciprocal of any quantity is the quantity thought of as a fraction flipped upside down. So the denominator becomes the numerator, and the numerator becomes the denominator. All right? So that's Article 51. And then lastly, Article 52 is not very important. The same letter accented is often used to denote quantities which occupy similar positions in different equations or investigations. So sometimes, instead of using different letters, the book might use a letter and then use a letter with an accent or with two accents and so on to represent a similar quantity. And again, that's not very common, but if you see it, remember to look back to our opening lessons to the definitions to understand what that symbolizes and represents. Okay? Now, that's all for our introduction to Algebra 1 from Articles 1 through 52. We've walked through all of the articles. I think things are pretty clear. These terms, one of the problems in modern algebra classes is the teachers and the textbooks. I'm not even blaming the teachers. because the problem starts in the textbooks. They don't pay enough attention to the definitions of terms, and then students are rushed into the next lessons, and they don't even know what the words mean that the textbooks are using or that the teachers are saying. Okay, so take your time and make sure you learn the vocabulary of algebra. It's very simple. Students just rarely take the time to learn it in the beginning, and then they spend their whole time in algebra confused because of vocabulary. So when you look back at articles 1 through 52, we look at some terms that are common in algebra, like coefficients, literal factors, monomials, polynomials, binomials, trinomials, dimension and degree, exponents, indexes, roots, and so on. Take the time now, before we get started, to learn the vocabulary so that as you get into the lessons, that's never going to be a problem. Okay? As I said, many students struggle with algebra simply because the teachers rush them into the higher lessons without ever making sure that the vocabulary is understood and clear. All right? Don't let that happen to you. Don't try to rush past the vocabulary into the lessons and then pretend you're confused and start saying that algebra is difficult. Algebra is not difficult. But as I said, one example that I guarantee will come up in your studies is that you will struggle with the order of operations. And if you ever ask for help, I'm going to say, go back to the definition of a term, look at the definition, and see that the solution to your problem with order of operation is right there in the definition of a term. That's what's causing the confusion. Okay, so my point is that as a classicist, I'm used to hearing people complain about how confusing mathematics is, how much time and attention mathematics takes because it's difficult. It's not difficult. It's just that in a philosophy class, as a classical teacher, we would spend a lot of time defining terms, laying all the groundwork for what we're about to discuss and get into in our studies, and then the vocabulary would be established, the communication would be clear, and we'd move one idea at a time through the study because the study is written by a great philosopher who's careful to do those things. Modern math textbooks, they're not written like philosophy books. They're not carefully organized. They're not carefully communicated. The teachers of modern mathematics are usually not careful, philosophically minded teachers. And so most of the trouble in modern mathematics and why kids in modern schools spend so much time on math studies is because the vocabulary and simple principles or elements of algebra are not carefully studied and taught first. So the textbook that we use does a good job of establishing all of the terms and vocabulary up front. It's one of the reasons why I chose to use it in the Classical Liberal Arts Academy. So take your time, master these definitions. I strongly recommend that you memorize them, all right? Learn the vocabulary, and you'll see that most of the trouble of algebra is avoided by carefully learning the definitions of terms, the signs used, and so on, before you get into the real lessons of algebra. That's all for this third lesson. We've covered articles 1 through 52. This is to be considered just an introduction. You now need to go and study those articles in detail. And again, I strongly recommend you memorize the definitions in articles 1 through 52. You'll be thankful that you did when you get into the later lessons. In your next lesson, lesson 4, you have a list of exercises to complete, which is going to test whether you understand these articles. And then we're going to get into algebraic addition and move forward. Okay, so I hope that's a helpful introduction to the first 52 articles in algebra, all the vocabulary you're going to need to get started. Time for you to get to work and master these lessons. God bless your studies.